Hello everyone, my name is Aidan Cranfield and today I'll be presenting on automated whitebox fuzz testing and we'll be focusing on the key concepts from this paper. Here's the outline for today's presentation. First, the background. We want to understand what fuzzing is, its types, and foundational concepts. Then we're going to look at Sage and take an in-depth look at the system created by Microsoft that applies whitebox fuzzing techniques effectively. And we're going to look at the experimentation and the real-world applications where Sage was tested, including some insights from Microsoft's findings. And then we're going to have conclusions where we summarize the key takeaways and the challenges and the future research directions inspired by this work. Let's start with some background. This paper was published in 2008 and is titled Automated Whitebox Fuzz Testing. It introduces Sage, a whitebox fuzzing tool. Now let's put this paper into perspective. In 2008, Microsoft's logo looked like this. The current version of Windows was Windows Vista, and it looked like that, very old. And this paper was authored by Patrice Godefroy, Michael Levin, and David Molnar. Now, a question you may ask is, what is fuzzing or fuzz testing? And we'll answer this on the next slide. Put simply, fuzzing is an automated technique to identify bugs or vulnerabilities in code by inputting random or malformed data. There are two types of concern when relating to this paper: black box fuzzing and white box fuzzing. As an example, consider this maze as your program. We can go in the direction up, down, left, or right, and consider the input, this input, down, left, down, right, and again, right the whole rest of the way. Sorry, down the whole rest of the way. We'll get this path. This input may be our desired way to get out of the maze. However, if you notice, there are other exits that may crash the program, and they look like this. So what a fuzzer will do is try all possible combinations of direction inputs and record if a crash has occurred. Now we could have a combination of down, left, and then down, and then right the rest of the way, which will look like this. Or the fuzzer may find this path instead, or finally this one. Now, one thing you may notice here is there are these exits right here. And these ones, if we were to do static analysis, which is static analysis specifically is looking at code patterns and not actually running the code to find vulnerabilities, and we may find these crashes. However, they're not even reachable, and we don't even have proof that we can get to them. Whereas fuzzing, we have that proof through the input. Now this leads us to a new question you may have, which is, what is black box fuzzing? Black box fuzz testing is a software testing technique that involves feeding a program with randomly generated or mutated inputs to detect vulnerabilities, crashes, or unexpected behaviors. The term black box means that the tester has no knowledge of the internal workings of the application and only interacts with it through its external interfaces, such as like maybe APIs, files, or network inputs. One analogy I like is a monkey on the typewriter. So we got monkeys on typewriters given infinite time and infinite paper, and they would eventually write a piece from Shakespeare. Now that is kind of the same here. Instead, we're looking for inputs, random inputs for crashes. So maybe the monkey will eventually find an input that leads to a crash. And how it works is the fuzzer generates random or semi-random inputs. The program executes and runs a test under these inputs. And then if the program crashes or behaves unexpectedly or reveals a security flaw, so maybe like a buffer overflow or something, the fuzzer will record the failure for further analysis. Now, some fuzzers may start with some more well-formed inputs and apply random modifications to increase chances of finding bugs, but this is the main thing we're talking about with black box fuzzing. Now, if you look at this code here, this function top, it takes in a character string, four characters long, and if we were just to do black box fuzzing, we would see that there are 5 values out of the 2 to the 8 times 4, which is like the 8 is the car size and 4 is the number of cars in that string. So there's about 5 of those values out of that will reveal an error. And the chances that we see is about 1 and 2 out of 30 chance to find an input that would create this crash. And this shows the limitation of black box fuzzing because it tests randomly and many parts of the program's logic may not be even exercised. And if a program contains a deep execution path triggered by only very specific inputs, black box fuzzing may not even be able to reach them. A concept that we need to know that will be needed for the rest of this presentation is constraint solving. Constraint solving is the process of determining values for symbolic variables that satisfy a set of logical constraints. It is used in symbolic execution to generate test inputs that follow different execution paths in a program. We can see that from this conditional here on the right, that we want x to be greater than 10 and x to be less than 20. The constraint that is extracted is that 10 is less than x, which is less than 20. Pretty simple. Another concept that we need to know is symbolic execution. Symbolic execution is a program analysis technique that treats inputs as symbolic variables instead of concrete values. This allows the execution to explore multiple paths in a program simultaneously by maintaining logical constraints on inputs rather than just executing the code with specific values. If we look at the conditional here on the right and apply symbolic execution, we can see that two paths appear. First, the system negates constraints to generate new test inputs to explore these paths. For example, if you look at the green box, we don't assign necessarily any specific value to x, we explore the path. So path 1 is if x is greater than 10, which we previously tested, we would then try negating that path and try x is less than or equal to 10 to explore the other path. And the process continues and repeats until testing different paths until all the paths are exhausted. And now that we know these concepts, we can ask a new question, which is, what is whitebox fuzzing? Whitebox fuzz testing is an advanced fuzzing technique that uses program analysis techniques such as symbolic execution and constraint solving, which we just talked about, to generate test cases that achieve high code coverage and efficiently find vulnerabilities. It uses symbolic execution. Instead of relying on randomness, it intelligently explores new paths by solving logical constraints. We also have a higher bug discovery rate. It finds deep bugs that black box fuzzers often miss. It has better efficiency. It's more likely to find critical vulnerabilities when compared to just purely random fuzzing. And just take a look at this code on the right because we'll be using it later. The function is top. It takes a 4-character string input, and if that input equals bad, exclamation point, where at least 3 of those are in there, then we get an error. So just remember that for the future. So something we need to introduce now that was developed, we will discuss the new algorithm to implement whitebox fuzzing called generational search. Generational search is a systematic search algorithm designed to explore different execution paths in a program during dynamic test generation. It efficiently balances between exploring new paths and also maximizing code coverage while mitigating issues with this, such as path explosions and divergences. Now on the right, we can see that this main loop search, and I'll take you through that very briefly. So the algorithm starts by initializing the work list with the seed input. It then runs the program and checks for failures, such as crashes, maybe memory errors. And then each input is expanding using this expand execution function, which you can see on line 8. We will talk about this function in the next slide as well. The new test cases which are the child inputs, are tested and scored, where higher scores are higher priority, and these are then added to the work list. Now this isn't all because we do need to talk about the expand execution part, and this symbolically executes the program and negates constraints to generate new test cases. This is the path for, which is the path for path exploration. And how it works is firstly we, in this function, we symbolically execute the program with the given input, and then it extracts the path constraints, which you see on the 4th line, which is PC, that variable, which records the branch conditions encountered during execution. The algorithm then negates constraints one by one to explore different execution paths, and the new inputs are generated based on the child inputs, which are returned and tested in search. So if we put this all together, we start with a well-formed input, and the search begins with this well-formed seed input, maybe like a valid file for a media parser, and this input is then placed into the work list. The program then executes and collects the constraints. The program runs with the seed that we gave it, and the symbolic execution engine collects constraints from these conditional branches. We then negate constraints and generate new inputs. The algorithm negates constraints to explore alternative execution paths, and a constraint solver generates new inputs satisfying these constraints. Child inputs, or as sometimes called generations, are created, Instead of performing a depth-first search, which explores all paths deeply before moving to the next branch, generational search generates multiple test cases at once, and it maximizes new inputs from each execution while avoiding redundancies like repeats. And new inputs are then prioritized. Newly generated test cases are ranked based on how much newer code they cover, and the higher scoring inputs are tested first to find defects faster. And then we repeat until a stopping condition is met, so the process continues until a time limit is reached or maybe no new paths can be explored. And now that we know this, you may be wondering, can you show me an example of white fuzzing actually working? Remember the code from before for the function top we see here? And the 0th step in whitebox fuzzing is to have an initial execution with the string good. So we're going to use good as our input, our initial execution input. And we can see the final count is 0, so we actually don't have any errors with this input. And then we can see good there on the input tree, and it's the 0th generation. Now we can move on to the first generation inputs. We start negating constraints, and when I say negating constraints, I mean that we use that path in our execution. And when we follow the inputs to test, we get goo, exclamation point, God with 2 Ds, Gowd, and Bood. And the final counts are shown here, and we can see that they're all equal 1. And these, so we don't get any crashes yet. And these inputs are now shown on our tree as the first generation. Now, we do the same thing as before, but for the second generation inputs. We take the first generation, we negate the constraints as to not have any repeats, and then we have the following inputs to test. I'm not going to go through all of them because there's 6 of them. And when we test, we see that for all of these second generation inputs, the count is 2. So we haven't found an error yet, but we're getting really close and we're on the second generation. And we can see in the tree, the second generation inputs always have 1 character different from the first generation. So if you look at let me rephrase that. If you look at the first generation input, GODD, which is the third from the left, right next to it is that input with a taken on different paths. So we get GOD exclamation point. And as you can see, all of the first generations have second generations to the right of it, and those ones have a 1 path difference. So in step 3, we test the third generation inputs. And by taking the second generation inputs and negating the constraints in a way that does not reveal any duplicates, we get the following inputs. We get GAD exclamation point, BOD exclamation point, BOW exclamation point, and BAD with 2 Ds on the end. And when we test, we get counts of 3. And for all of them, means they're crashing. So we found 4 of the 5 inputs that cause an error to occur. Now since there are 5, there's 1 more, and that is bad, which will be found when we take bad exclamation point when we take bad with 2 Ds and negate the final constraint, and then we get the final error input, and we found all 5 inputs that cause an error. Now that we know about fuzzing, black box and white box, the generation search algorithm, and the terms that go with it, we can now move on to the next section, which is SAGE, which stands for Scannable Automated Guided Execution. This is Microsoft's first implementation of whitebox fuzzing. Firstly, I will define SAGE, which is, yet again, Scalable Automated Guided Execution. And it is Microsoft's whitebox fuzzing tool that systematically explores execution paths in binary programs using symbolic execution and constraint solving. It is designed to automatically find security vulnerabilities in large-scale software by generating intelligent test cases that maximize code coverage. With that out of the way, now we can talk about the architecture of SAGE. So for phase 1, we have the tester, and it runs the target program with an initial seed input. It then observes the execution for crashes, memory violations, or unexpected behaviors like infinite loops, etc. And then it records these failures for further analysis, and if no crashes occur, then we move to the tracer phase. Now in the tracer phase, it records a complete trace of the program's execution at the x86 instruction level, and it uses Microsoft's iDNA framework to collect data on every executed instruction, and it logs the program processes as its input. Now, why do we do this? Unlike source-based tools, Sage does not need access to source code, and it works on binary executables, making it suitable for real-world applications. So next we go to the coverage collector. Now it replays the execution tree and determines which code blocks were executed, so like which parts of the program ran. It helps determine how much new code was tested, how much new code each test case covers, and then it uses this information to prioritize test cases that explore new execution paths. And then lastly, in phase 4, it replays the trace and it tracks the symbolic values for these independent operations. And then it extracts constraints on symbolic inputs, and then it uses a constraint solver to generate new test inputs. So you may be asking, why this design? Well, number one, there's no need for source code. It works on any Windows executable. 2, deterministic replay. The recorded execution ensures a consistent analysis. And then there's no runtime overhead, so the program runs at normal speed as the symbolic execution is done offline, and we'll explain that in later slides. So, trace-based x86 constraint generation. So the key idea here is that Sage performs symbolic execution at the machine instruction level. Instead of modifying the source code, it does this. So why use the x86 binary instead of source code? Well, number one, it works across different program languages. Source-based tools need different versions for C, C++, Rust, Python, etc., etc. So Sage works without any Sage works with any compiled Windows program. Number 2, it avoids issues with compiler optimizations. Compilers optimize and modify source code, changing its structure. Sage analyzes the actual binary that runs so that compiler optimizations don't change the code in any way. And number 3, it works even without source code. Many programs rely on third-party libraries whose source code is unavailable, and Sage may analyze the closed source binaries to allow it to execute its function. So now I come to this. Why use offline tracing instead of runtime instrumentation? Number 1, there's no performance overhead. Many fuzzers insert extra code to track execution at the runtime, and that slows down the program. Sage records executions first and then analyzes it offline. 2, it handles non-deterministic programs. Some programs behave differently on each run. For example, due to like randomizations in the code or certain network inputs like that. And then Sage replays the exact same execution, ensuring that there are accurate results. So now we're going to go to constraint generation in Sage, and we're going to look at some assembly code and how it generates those constraints. So constraint generation in Sage extracts constraints from the x86 instructions and branches. The key idea of this is that Sage tracks a symbolic value for input-dependent operations and builds logical connections to systematically and precisely explore new paths. So how symbolic execution works in Sage is the following. If we use this example of the code, we see that a 10-byte file is put into a buffer starting at address 1000. So address 1000 to 1009, which is 10 bytes, are stored symbolically as input 0 is like 1000, and then input 9 is like 1009. And then the byte address that corresponds to 1005, you can see the register AL holds the input 5 symbolically on line, what is that, like the third line down. And after executing this, that AL register holds the input of 5 symbolically. Sorry, I just said that, but then what it'll do is it'll add one of two constraints, t equals 0, or where t does not equal 0, where t equals the input minus 5. So now we know that the architecture of Sage and how it works in the x86 instruction set environment. We can move on to the experimentation carried out by the authors and how they analyze that. So now we can move on to the experimentation section. So now we're going to go over some initial experiences, specifically with the MS07017. So to give some context, there existed a bug in code that parsed ANI formatted animated cursor files, and previously black box and static analysis had failed to find this bug. Now, the root cause of this, that the vulnerability was due to some incomplete validation of the size parameters in ANI records. And black box fuzzing failed because it couldn't generate complex enough inputs to trigger the bug, which was requiring that they had 2 ANI-H records. Now, what Sage did is it found the bug within hours, starting with a well-formed ANI file, which is on the left. You can see there's 2 files, the one on the left. And then it systematically explored the execution paths without prior knowledge of the ANI file. And then it found determined that having 2 ANI records caused the bug. As you can see, that I have on the right side, there are 2 records highlighted. Now, some other experiences with other applications, that was initially tested on was an Office 2007 application, and it generated 4,548 test cases, and 53 of these test cases caused the application to crash. The crashes that were investigated were null pointer dereference errors, and they show how Sage can successfully reason about programs on large scale. The researchers used Sage to parse media files on 4 popular file formats, media parsers on 4 popular file formats, and Sage found various read violations and demonstrated that Sage had the power to infer file structure from code. The researchers also used Sage to test a tool that handled compressed formatted files. And these are previously tested extensively with black box tools. But Sage was able to find 2 new bugs, specifically one Stack Overflow bug and one infinite loop bug that caused the CPU utilizations to be constantly at 100. So now for some more about the control of experimentation. So these experiments were precisely controlled so they can analyze certain things about Sage. So the test plan focused on 2 media parsers, media 1, media 2. They didn't name them, just that's their names. And they used certain input files. So they had 5 well-formed input files from known libraries, and they created 5 bogus files. And media 2 only used bogus 1. So here we can see the bogus file examples. Bogus 1, 100 0 bytes, and then it increases, and then bogus 4, you see it has 100 random bytes, bogus 5, 800 random bytes. So the execution details, each Sage search ran for about 10 hours using a 32-bit Windows Vista on AMD Operaton 2 GHz processors with 4 GB of RAM. So pretty powerful for back then, I think. And then crashing tests were then bucketed by stack hash. So what the stack looked like, they hashed it, and this was a unique identifier based on the crash point. And this identifier was helpful determining whether crashes came from the same bug. So some results and observations. Now, symbolic execution tasks were noted to be slightly slower than regular program testing. Not slightly, significantly slower than regular program testing or tracing. So here we have the example. In the media 2 experiment, and there's a case where symbolic execution averaged at a time about 25 minutes per task, and regular tests did this in just like a few seconds. But why it's still efficient? Sage is more efficient because, despite being slow, the symbolic execution is only a small part of the total search time, because one symbolic execution generates many test cases. And in a case, 25% of the total time was spent on symbolic execution, and this shows that generational search makes an excellent use of each expensive symbolic execution task. Another thing they found is that when they were comparing generational search to depth-first search, they found that generational search is much better than depth-first search. So just to go back, generational search explores multiple paths at each generation, maximizing coverage and bug discovery, and depth-first search focuses deeply on one path before exploring others, which can cause inefficiencies. Now, there was a 10-hour run of depth-first search to find bugs, and it failed to find a crash in media 2 at all, whereas generational search just found a crash within minutes. Then depth-first search again suffers from these pathological divergences, whereas generational search handle these divergences by prioritizing high coverage paths. That's that um, scoring part of paths. Another thing they found is that well-formed inputs are better than bogus. In the Media 1 test, 6 of the 10 input files found bugs, where of those 6, 5 of them were already were well-formed. So only one of them was a bogus file. In Media 2, 4 of the 6 files found bugs, so it used 6 files only, but all 4 of those were well-formed. So the conventional wisdom still holds that well-formed should be a starting point for white box fuzzing rather than just random inputs. And now we can move on to the conclusions and start wrapping this up. So for the conclusions, some key contributions. The researchers introduced generational search for dynamic test generation, and this was applied in their SAGE testing tool. So now at Microsoft, Whitebox and Blackbox testing are used to extensively test all of their software going forward from when was this, 2008. And some feature work the researchers mentioned was that they were optimizing search strategies and wanted to combine certain search metrics to make it more efficient. And now we can move on to questions. So let's say you have some questions. What do? The answer? I recommend you go read the paper. Thank you very much for listening.